In these sections, we'll look more at determinants, some of their applications, and other uses. So I've mentioned this in the last time, that a square matrix is invertible if and only if the determinant is not 0. So this can be added to our big list of things from the invertible matrix theorem. In this first exercise, we are given 3 columns, A1, A2, and A3, and we want to know if the matrix with all those columns is invertible or not. So we have many things we could do. We could take this and row reduce it and see if we get the identity, but we're going to do it another way. So I'm just going to look at the determinant of this matrix. So I'm going to use that shortcut method for the 3x3. So I rewrote the first 2 columns. I'm going to multiply down each of these, and I'll get 0, 70, and then 42 times 3. Then multiply up. Get 0, 1 negative 140, and 42 times 2. And I always think of it as bottom minus the top. So bottom minus the top. So we get that the determinant is 0, which tells me this is not invertible, or A is singular. Part B says, is the set linearly independent? So the columns of my matrix A cannot be independent since the determinant is 0. So same idea, I just have 4 vectors in R4. I want to know, is this set linearly independent? So again, the first thing you should do when you're asked if a set is linearly independent or not is just to look at them, see if you can see a dependency relationship. I don't see one right away, so we'll use determinant for this, and I'm going to do cofactor expansion about the last column. So I realize it's not quite in matrix form. So I have negative 1 to the 4 plus 4 power times 2 times the determinant of 3 to negative 2, 5, negative 6, negative 1, negative 6, 0, 3. Negative 1 to the 4 plus 4 is positive, so this is 2 times the determinant of all this stuff. So I'm going to do cofactor expansion again. I'm going to do it about the 3rd row. Negative 1 to the 3 plus 1 times negative 6 times the determinant of 2, negative 6, negative 1. I'm going to say plus 0 plus negative 1 to the 3 is in the 3rd row, 3rd column, times the determinant. When you cross off that 3rd column, you'll be left with 3, 2, 5, negative 6. Negative 1 to the 4th is positive, so I have a negative 6 times negative 2 minus 12 plus, I forgot my 3 in here, 3 times negative 18 minus 10. 2 times negative 6 times negative 14 plus 3 times negative 28. This determinant is 0, which tells me the vectors are linearly dependent. We have seen several different ways to solve a system of equations. We can augment and row reduce. We can find the inverse and do A inverse times B. And Cramer's rule is just yet another method for solving a system. This tells you the formula for it. So I will apply that formula using Cramer's rule on this exercise. All right, so it says x sub 1 is equal to the determinant of A1 of B divided by the determinant of A. The A is the coefficient matrix, so the determinant on the bottom is 3, -2, -5, 4. And on the top, the determinant of A sub 1b means replace column I with column B. So replace column 1 with the B. So this is determinant of 6, 8. So that's replacing my column 1 with the B and leave the other one alone. So we have 24 plus 16 over 12 minus 10. So 40 over 2, which is 20. So my x1 is 20, and then x2 would be the determinant of 3, -5. Replace column 2 with your right-hand side, divided by the determinant of the coefficient matrix. So this is 24 minus a -30, and this is still 2. So we have 54 over 2, 27. So our solution, x1 is 20, x2 is 27. So I personally just find Cramer's rule just kind of cool, just as a different way to do it, and makes you wonder, well, why does that work? I don't know that I've ever really seen anyone use this method computationally or theoretically to actually solve. So to me, it's just kind of a cool alternate method. The next part of this lesson will be more on how row operations affect the determinant. So we have 3 different types of row operations, and here's how it affects the determinant. So if a multiple of one row is added to another row to produce matrix B, then the determinant of A and B are the same. If 2 rows of A are interchanged, so if you swap rows, then the determinant is affected by a negative sign. And then if one row is multiplied by some constant, then the determinant is also multiplied by that constant. So if we're given that the determinant of this matrix is 7, how would you find the determinant of this modified by one row operation? So notice this row operation is it took row 2 and it added 3 of row 3. So it added a multiple of another row. So that means the determinant did not change. In B, notice that row 1 and 3 were swapped. So that changes it by a negative. And then row 2 is multiplied by a 2. So this would be a -14. So if we have a 5 by 5 matrix and the determinant of this 5 by 5 is 10, to find the determinant of 2 times that matrix, notice that every row is multiplied by 2. So every row is going to be multiplied by a factor of 2. So there's 5 rows. Or you can think of this 2 to the 5th times 10. Sometimes you can find determinants quickly if you do a couple row operations, if you know how the row operations affect the determinant. To use row reduction to find the determinant, our goal is to use row reduction to transform it into a triangular matrix. So I'm going to try to make all of those zeros. So I'm going to do row 2 equals row 2 plus 2 row 1. Row 3 equals row 3 minus 3 row 1. And row 4 equals row 4 minus row 1. Notice in all of those, I'm adding a multiple of another row, so the determinant does not change. At this point, I notice that row 3 and row 4 are the same, so I'm going to add them together. I know that if I have a row of zeros, that my determinant is 0. Think about doing cofactor expansion about the bottom row. Just some other little results. Theorem 5 says that if you have a n by n matrix, then the determinant of A equals determinant of A transpose. And really you can think about this because of the cofactor expansion can be about a row or a column. So doing it on A transpose would be the same as doing it on A. And then also, if you have the determinant of the product, that is the product of the determinants. Again, this is a very nice property for later when we do diagonalization.